BSides DC would like to thank all of our sponsors, and a special thank you to all of our speakers, volunteers, and organizers for making 2018 a success.
My name's Bobby Filer, and I'm going to do the talk right before lunch on bringing red versus blue to machine learning. Just a little bit about me to kick things off. I do data science at Endgame. If you guys don't know who Endgame is, we're an endpoint security platform. We have some machine learning baked in. I'm part of that team, so I do a lot of machine learning for usability, things like conversational interfaces, adversarial machine learning, which is really the basis of the talk today, and then malware classification, which is one of our flagship features within the product. One kind of cool thing I was able to work on this year, really at the beginning of the year, was a paper called Malicious Use of AI, was really the thrust of it. And it was a combination of academics, industry folks, and nonprofits going into kind of a scenario-based adversarial examples for cyber, politics, military, physical systems, things like that. It was super fun to work on and kind of got me thinking about this idea of, you know, how red teams and blue teams in today's security spectrum tackle kind of this machine learning issue. So I've given talks like this before at more machine learning specific conferences, and there was a ton of math involved. I wanted to take a step back and go a little bit more high level, explain terminology, nomenclature, strategies, and then for consumers of machine learning security technology in the crowd, or people kind of considering purchasing this, I wanted to give you scenarios that you need to be cognizant of, as well as potential questions you may want to ask a vendor when their marketing team inundates you with like ML solves everything. So hopefully you get some value out of that. And then I'll cap it all off with hopefully a strategy base, like here's what red teams could consider, blue teams, and then finally purple teams. So my motivation for doing this is really twofold. I've been going to security conferences for about a decade, and I've always been super envious of people who get up here and drop like exploits or talk about vulnerabilities. I think it's black magic for the most part. It's super cool. And I was a little jealous of people who get to do that day in and day out. But about 2-3 years ago, adversarial machine learning kind of came out, particularly targeting computer vision. And I was like, you know what, maybe it's our time for data scientists to do kind of this vulnerability research and red teaming. And I got really excited and started to dig into it a little bit more. But the other reason is maybe even more important for you in the crowd. It's this idea that machine learning has become so pervasive in security stacks, and there's been maybe a little bit of a rush to claim table stakes for this technology. More and more vendors are trying to implement it, to get it on their website, to promote it at Black Hat and RSA, that this rush job could potentially introduce new threat vectors and potentially make security a second-class citizen, which for, I'm guessing everybody in here, is an opportunity to potentially poke, prod, and exploit. So I'm hopeful that you know, my background and the story that I'm hopefully able to weave today will provide some insights there. But before we dive into adversarial machine learning at large, let's go into how machine learning is being applied just within InfoSec. Machine learning can kind of be thought of as just a fancy rule in the grand scheme of things. So if you have kind of what you have on the slide here, which colors don't come up very well, but you have blue dots and red dots, good dots and bad dots being red. And you know that these are binaries, and you want to devise some sort of rule or logic or something to delineate those. You could do something like at the bottom part of the slide, write a YAR rule that says if you see this many registry keys in the strings and the file size is a little bit smaller, let's call it bad. And it will paint the feature space kind of in a 2D plane, that red color. And it does a pretty good job. It covers, I'd say, the majority of the red dots. It unfortunately leaves some out and incorporates some blue dots. And that's the whole false positive, false negative problem that machine learning is attempting to solve. And it solves it, I think, reasonably well. That's a super biased opinion as somebody who uses machine learning every day, so fair warning. But what it allows you to do is leverage automation and kind of this logic or intelligence to identify these kind of latent relationships that exist between features and samples in your data set that you would kind of be unable to figure out on your own using a pen and paper. And what you're able to do is machine learning can be thought of as like a fuzzy, more sophisticated rule. And instead of drawing that nice rigid box on the screen, you get this little slopey, less crunchy decision boundary. And you can see it envelops more of the red while leaving space for samples that it hasn't seen before. So this ability to generalize is another important thing that machine learning can bring to the table. And it does that reasonably well. For things like email security, one of the very first things I worked on was spam detection. If anybody's taken like a data science 101, you built a spam detector, that's almost a given. Things like identifying C2 beaconing, DGA detection, or DPI to identify malicious content is all leveraging machine learning now. UEBA is probably maybe the most heavily marketed thing. Anomaly detection is incredibly difficult. I wouldn't say that it works 100% of the time, but maybe 60% of the time it works every time. So that's not so bad. And then finally, MySpace, which is endpoint protection, leverages it for something called next generation AV, which is a super fancy way of saying just not traditional AV. And if you're interested in checking that out for free, jump on VirusTotal and grab a handful of samples and throw them at the wall, and you can start to see how these traditional AVs versus next-gen AVs label these samples. And you'll find that for the most part, traditional AVs, when they're right, they are right 100% of the time. And that's the luxury they have with signatures. But as new stuff comes in, you'll find that next-gen AVs kind of claim it's bad earlier. And VirusTotal has a very cool thing where you can see over time how predictions change. And you'll see AVs catch up in a lot of ways to machine learning, which is, I think, very, very interesting and really good for the security community. No more hitting that. So, all right, adversarial ML, foundation of this talk. What does that mean? At its core, it just means, can we break machine learning? And the answer is, yeah. I mean, it's not exactly trivial, but it can be done. And a nice, tight example that I like to give is you have this machine learning model for malware. And it has a handful of features plucked from, PE header, imports, exports, maybe some byte level information. And it does really, really well. So well, in fact, that you could use it on your desktop or within your enterprise. But what we're trying to do with adversarial ML is make structural changes to the binary without breaking it or without changing kind of what it does at its core, which seems extremely difficult. And sometimes it can be. But other times it can be just changing a section name or unpacking it or maybe adding a string or two. When these things happen, my job becomes really, really difficult and we run around with our hair on fire for a little bit, but it's still incredibly good to know these things. And that, at its core, is really what we're trying to do with adversarial machine learning. And we're able to do this and take advantage of these vulnerabilities, and this is where it gets a little theoretical and mathy, by taking advantage of the distribution space of whatever problem you are trying to tackle with machine learning. So let's say it's malware classification. That's an easy one to wrap your head around. You have this whole distribution space of every binary that's ever existed. How can you possibly capture that if you are a data scientist building a malware classifier? The answer is you're not going to. You're going to try to capture some sort of subset that gets the gist of it, tries to generalize. But that's really only representative of a pocket or a percentage. And you train your model on that, and it does reasonably well. Then you have your test data that you have. And there's a small overlap between test data and training data. But for the most part, training data sits outside of that distribution. And that pocket, and you can kind of see the little crescent shape that's white there, is your adversarial space. It's things that your model just simply doesn't know about and can't possibly compute. And that's the area, that sort of crunchy space that you can take advantage of. And you can see it more realistically how a model would interpret it over on the right-hand side, where you have the neural network that draws that nice wavy boundary, and it does a really good job of separating the good and bad. But then when you look at your data and you look at the mode, and it kind of cuts right through linearly, it opens up all these little pockets that allow the classifier to maybe be blind and presents an opportunity for exploitation. And there's probably no better example of this than, who here's seen this example? Anybody? All right, more than I expected, so that's great. So this is like a super famous one from Ian Goodfellow, who is like the father of this research. But the idea is for attacking an image classifier, you have a picture of a bus, and then you inject noise. And this noise, I mean, it looks a little staticky there, but when you overlay it or add it to the image, you really can't tell a difference. But to the classifier, it's completely different. So you go from a bus to an ostrich. And there will be a couple more examples of this in a little bit, but it is a thoroughly fascinating branch of adversarial research. And what this does is this takes advantage of things like blind spots, and will do things really to make it as straightforward as possible to exploit. And as you'll see in a little bit, oftentimes you don't even need direct access to the model you're attacking. You can create a substitute model or something that looks like it and exploit kind of this notion of transferability, which hopefully the example I give in a little bit will drive that point home. We're going to walk through kind of the nomenclature now, just so everybody has an idea of what I'm talking about. And I encourage you, like if you're interested in any particular thing, screenshot on your phone, write it down, Google it. There's a ton of research in this space. The papers are really interesting. They tackle things from biometric systems to malware classification to self-driving cars. The whole gamut. So whatever piques your fancy there's probably some research in it. But the two primary or foundational attacks in adversarial machine learning are these ideas of exploratory versus causative. And exploratory really seeks to just evade the classifier, find these blind spots through querying, probing, whatever, making manipulations, and then throwing it back at that same classifier. You don't have any control over training data or anything like that. You don't necessarily have a bunch of knowledge of the underlying structure, like where the training data came from, what models they're using, parameters, anything like that. Whereas causative is something that's maybe a little bit more familiar to people in InfoSec. It's this idea of model poisoning. So getting into the training data and being able to influence that little wavy decision boundary I showed earlier by kind of tweaking samples and throwing them against the wall. So spam detection is a good example of that. You have these systems that look at stuff on a online basis or real-time basis and constantly change their prediction and how it's made. And these sort of attacks, these poisoning attacks, will say, oh, well, if you say, click here for free stuff, then I know it's spam. And then they change it to like leet speak, and then it bypasses, because over time, the model changes its decision boundaries and everything else. So the next thing is really trying to capture the knowledge space of an attacker when targeting your machine learning models. This idea of black, gray, and white box attacks. And black box, as you can imagine, is this idea of like no knowledge of what you're targeting. So this means no knowledge of the algorithm being used. So you don't know if it's deep learning or a random forest or anything like that. You're relatively unsure where the training data came from. Really, the only thing you know is that you know the task that it's meant to do. I mean, you're attacking it for a reason, so you know that it's either trying to classify images or identify malware or something like that. But that's really it. You're for all intents and purposes, flying blind. Gray box, I'll show an example of in a little bit. This is limited knowledge. This means that you're able to pull or tease out a little bit of information. So this could be maybe a blog post that talks about where they got their training data from, which wouldn't be very smart. It happens, whatever. Or maybe a more realistic scenario is instead of just giving you back like, this is a bus, or this is a piece of malware, it says, this is a piece of malware and I'm 87% sure. So that little nugget of information, that 87%, is hugely important. And I'll kind of walk through how you go about exploiting something like that. And then finally, you have white box, which is what a lot of us in this room, if you are building data science models and then performing adversarial machine learning, what you would be doing. You have direct access to the model, you know where the training data is coming from, you know all the parameters, you have kind of the keys to the castle. And you can hope to elicit some sort of knowledge from that. I'm not even gonna bother. It's too early. So adversarial specificity is really just the difference between targeted versus indiscriminate attacks. Targeted, the best way I like to describe this is, I have something that's a dog, but I want it labeled as cats. This is, you have something and you want it to be called something very specific that is not what you have. Where indiscriminate is more or less like, I really don't care what you call this picture of a dog, as long as you don't call it a dog. That's the whole spectrum of that. Frequency, as you can imagine, you have a couple different things. This actually deals more with, I think, traditional red versus blue, where you have a single opportunity to exploit something versus, multiple opportunities. So one shot just means you get one chance to throw it at the model, learn something, and then the next time you have to get it right, or it's a lost opportunity. Naturally, there's a lower barrier to success there. But in real life environments, that's kind of the only option you have. Where iterative is you can kind of go back and forth playing 20 questions with the model and refine your exploit sample to eventually bypass. So some kind of fun attack examples that have come out in the past couple of years that I always like to talk about are things like adversarial glasses. So some researchers at Carnegie Mellon got some 3D printing tools, and they built these glasses that look kind of tie-dyed. And when you put them on and went in front of a camera that went to classify celebrities, it went from classifying you as like some guy with glasses on to Mila Jovovich. And there are a ton of examples of this sort of idea working. It's this idea of just slightly perturbing what the classifier is expecting to get a vastly different response than you were expecting. And adversarial patch is really a continuation of this and arguably much more dangerous. It's an idea that you could print out a sticker and throw it on a stop sign, and suddenly it's being read at, not stop, but speed limit 45 miles an hour. Or if you have something that says, is this a banana? And you put it next to it, it says, no, it's a toaster, which is a much, I guess, funnier example. But these things are, I think, a major concern, and there's a lot of folks in the self-driving vehicle community that are actively researching this and trying to develop countermeasures. And then finally, just talking about how, I guess, effective changing one little dot on an image could be. Some researchers came out with something called one-pixel attacks, where they were able to manipulate or more or less just white out a single pixel on I think a 256 by 256 image. So it's not super clear by any stretch. But it went from being able to classify ships with near 100% accuracy to calling it a car, or a horse, a frog, deer, an airplane. So you can start to see how effective this could be with just minor perturbations, which is, I think, really, really interesting. But adversarial machine learning isn't necessarily just attack. There is a bunch of research in the defensive use cases, arguably not as fun to talk about, but important nonetheless. These fall into two primary categories. Kind of the proactive, where you attempt to make the model more robust prior to ever being attacked. Things like adversarial retraining, which you'll see an example of, distillation, leave one out, all these things to try to reinforce and make your classifier more robust to attacks. And then the second one is probably the one that is much more doable for anybody in the audience and really even me in my day-to-day. It's reactive. So how can you detect adversarial examples after they're already in your environment and being thrown against your model? So that's things like developing a secondary classifier or anomaly detection for anomaly detection, which seems insane, but kind of what you have to do in these situations, or input reconstruction. So if you think about the one pixel attack that you saw up there, you could run like autoencoder denoising to try to lessen the perturbations and make it a little bit smoother for you to classify correctly. So adversarial retraining is probably the one that gets tossed out the most, is the go-to most effective approach to beating or at least attempting to stave off adversarial examples. All this really is, and it's kind of broken down here on the right, is you have your training data and you build your initial model. Then step 2 is you yourself kind of purple team it and you create your own adversarial examples against the model you just trained. Then you, if they're effective, you roll those examples into your training data, retrain, and then suddenly you're more robust because of this augmented training data set. And this is pretty effective. It works extremely well against one-time attacks, as you could imagine, but anything where you get multiple opportunities, you're still not in the best place. You're just giving the attacker too many opportunities. And what that really does, in the grand scheme of things, is once you go down this path, you're really just setting up kind of this game theory arms race between you and a would-be attacker. And it kind of brings you to this idea, and this is used in a bunch of different domains, but within adversarial machine learning, this no free lunch problem, where you have this trade-off between being super accurate or super robust against attacks. And adversarial retraining on the previous slide is a good example of that. You get better at staving off attacks, but you sacrifice some accuracy or classification performance due to that. And that sort of decision that you have to make is really an interesting one, particularly within the information security domain and red versus blue as well. And what that kind of lays out is really this, I called it an arms race earlier, but it's just, in the grand scheme of things, an unfair advantage for the attacker. And I think anybody in here, data scientists or just SOC analysts, whatever, would probably agree with that. It's way easier to be offensive than defensive person. And the reason why, and two that I'd call out kind of on this table, is on the defensive side for machine learning, you're really only as secure as your weakest link. And for offense, it's just finding that weakest link and exploiting it. That kind of sucks. And the other one that might make any marketing people in the audience cringe a little bit, but on the defensive side, you need to be almost 100% perfect, right? Or depending on if you're looking at materials, like 99.99% accurate. But then on the offensive side, it's like, I don't really care. As long as like 10% of the time it works, I'm good to go. Like, this is a low-cost attack for me. I'll give a couple of different examples of how easy it is to just spin up these examples, and they're mostly throwaways, but when you find one that works, then you're pretty much good to go. Which brings us to hopefully the point where everything I just told you will be reinforced in a way that is both pertinent to you and hopefully a decent example. So let's do scenario 1. Congrats, people in the audience. You just bought a Pew Pew endpoint platform with next-gen AV baked in. It's awesome. It's almost definitely going to stop every piece of malware you could ever have in your enterprise. And the vendor put it in VirusTotal. They're super confident. This is all great. The best part is they put it in VirusTotal and they provided a score because they wanted to show you how confident they were in every decision they could possibly make. So for you as a would-be attacker, the threat model here is you kind of have limited knowledge. It's like a gray box situation, but it's potentially iterative because they have it on a third-party website, which is great. So you attack that as opposed to attacking the real-world platform. So what we're going to do is we're going to attempt to build an agent-based platform that probes this model on VirusTotal and attempts to craft adversarial examples that beat it. So what does that look like? It looks like it might have froze. There we go. All right. So what we're going to do is construct kind of a game. And this approach was taken by researchers, I think at Google Brain, OpenAI, a few others, to beat Atari games like Breakout. This idea of using reinforcement learning where you have your environment. In Breakout, it's the Breakout game, and then the scoring mechanism. So you move your paddle, and if you knock away blocks, you get a reward. That reward is some sort of point system. And if you don't break any blocks, you don't get a reward. And you do this tens of thousands of times until you learn the best approach of where the paddle needs to be. For our problem, we're going to replicate that same thing. Our environment is the next-gen AV in VirusTotal. Our reward is the confidence score. Can we make the confidence score go down instead of up? And we're going to make non-PE header breaking changes. So things like adding imports, changing section names, appending zeros to the overlay, something like that. And we're going to do this over and over and over again until we kick out an example that falls below the threshold and is called benign. So we did this at endgame, and it was reasonably effective. Black box attack kind of against a model that we faked kind of in VirusTotal. We created samples and then threw them back into VirusTotal, and we were able to fool like 10, 15, 20 vendors at a time doing this approach. And it's kind of neat that you can do this. Again, this is relatively low cost. We have code, if you want to check it out, on our GitHub. So you could start playing around with this. It's kind of an interesting idea. And you can drop in whatever classifier you want. That way you aren't breaking any sort of laws or licenses, anything like that. But yeah, so on the red side, it's relatively straightforward to do this. On the blue side, though, what can you do? I mean, they're attacking a model kind of in a space that you have only a slight purview in. But what you can potentially glean is you can start to look at, you could replicate this yourself and start to look at what I call recipes that were thrown out as the most effective. So what changes were most commonly recommended for ransomware to go from ransomware to benignware? So this is things like unpacking, appending to the overlay, section renames, or you could look at viruses. 10% of the virus samples we threw at this platform were able to evade eventually which recipe was the most effective. Adding a section, adding or appending to imports. Understanding this will let you better understand which features within your model are potentially the most, I guess, prone to exploitation. And you could either dampen those, which is an option. You could remove them completely, or you could try to go the adversarial training approach, generate a bunch of these examples, throw them at your classifier, and then boost it that way. So a couple different options there. All right, case study 2. This is my favorite one. Your company just purchased Deep, the deepest deep learning you could possibly have. Doesn't even need features. Just throw the whole thing in there, and it will get it right 99.9% of the time, because that's how these things work. Their website has no real information on it. It's just pretty much all marketing. So you aren't able to derive any real OSINT there. Also, it doesn't provide any sort of score. It's just a good bad. So they actually did a good job there. Your threat model for this is black box. It's a one-time attack because it's kind of in platform. It's available as is. So your goal in this case is to try to exploit this idea of transferability, where you create a substitute model that you think is close enough or sits in the same space as the model you're attacking, and they may share the same feature space, and you can exploit them. It sounds insane, but it actually does work. So how does it work? The main thing is trying to identify training data that would be around the same distribution of the deep model, which seems difficult until you think about something like malware classification, and you realize like there's only so many places you can get malware. So you can start to pull that down. You can get a representative sample, and then you could do something like create your own model or link to the bottom. You could use code like malconv, which is a nice open source deep learning malware classification model. And what you do is, once that model is up and running, you attack that model. You don't even worry about the deep model at all. And you attack it over and over again until you get nice, juicy adversarial examples, and then you can throw them at the target model, the deep model, and more often than not, it'll actually work. It's kind of this crazy idea that when you deal with a finite number of features, in this case, probably 256, because it's reading in just all bytes. There's only so many places you can go, so many places you can run and hide in this situation. So any model you create that is relatively similar to another model you are attacking, those examples could potentially transfer over using this approach. And if you're interested in trying to carry this out on your own, like I said, malconv is awesome. It was designed by, I think, some Booz Allen researchers. And then if you want data that's relatively distilled down and not just full-blown malware, we have a data set called Ember, which is already featureized. I think there's 1.5 million feature vectors there of goodware and badware that you could use, and you could basically recreate this entire setup. All right. As far as defending this, it's kind of bleak in the grand scheme of things. This is not a feel-good story by any stretch. You could do adversarial training. Again, you probably sacrifice performance. Again, you get yourself in this arms race of trying something, and then they just come back and try something else. An option that has become a little bit more prevalent lately is distillation, which is a compression technique that is super mathy. I won't go into hyper specifics here, but you basically replace the good and bad labels with probabilities and then retrain. And then the decision boundary that you ultimately create is less kind of jagged and much smoother. And it becomes a little bit harder to find those little crunchy points to exploit, those adversarial pockets. Neither of these are silver bullets by any stretch. Best case scenarios, it slows the attacker down for a little bit, which at the end of the day is probably still a win. Because it's just way too difficult to capture every possible permutation that you could see in a malware classification example, any sort of network attack example, really anything like that. Okay, last case study here is a poisoning attack. You just got an IDS called Red Herring Inc. He uses online learning, so a classic anomaly detector scenario. What this allows the vendor to do is save a bunch of resources because it can start to identify stuff in real time. It doesn't necessarily need to be brought back and manually retrained. The threat model here is more of a white box, so you are much more familiar with everything associated with this model. It's an iterative attack surface. It's something that you can continually poke, prod, and throw examples at and hopefully exploit. The exploit in this case, though, is trying to push that decision boundary in one direction or the other so you can start to introduce classification errors, which lessens the confidence. So think of the spam example where you are allowing spam to get through, and then people eventually are just like, I'm tired of this, it doesn't work, and people turn things off, which is really one of the goals of a poisoning attack. A good example of this that was not security related, just funny, was Taybot. If you guys are familiar with Microsoft's super racist AI that came out. It was, honestly, best intentions there. But yeah, Twitter, as it turns out, can make people and even AI go a little crazy. So the attack strategy here is super straightforward. You have your training data, and all you're doing is injecting kind of chaff in there. Things that are a little perturbed, that, like I said, once you identify that decision boundary, it just pushes it up or pushes it down a little bit. And then once you get it into a good enough place, you just kind of say, I'm good with this, it's misclassifying enough that I consider this poison, and we're done and dusted. So this, you can't see that well, but so the idea here is you start with a decision boundary, kind of the black line that is highlighted in step 1, and what you do is you throw those 4 or 5 stars over at the 0 axis on kind of the Y axis, And you do that kind of over and over again, and what that does is these examples to somebody monitoring it don't seem particularly anomalous. They kind of sit right along the decision boundary. But what this does over a series of iterations is it moves that decision boundary up, and then it creates a pocket where you could eventually take advantage of it. And that, at its core, is really what the poisoning attack is trying to do. If you're interested in this code, actually came out of Clarence Chio's Safari book. I think it's like Security ML, which is very good. There's an entire chapter kind of on adversarial ML, focused solely on these examples, and it's a great way to gain even further intuition kind of in a Python environment. Defending poisoning attacks. This is my one very antiquated meme, so this is full dad mode here, but really, you have a couple different options. One is super mathy, where you do dimensionality reduction, and you try to take the features and put them in a feature space that the attacker just can't comprehend. You just make it more complex. This would work, at least slow them down again until they gain more knowledge, and again, you have the arms race problem. The one that's kind of captured on the right is you could monitor inputs, see if a single input or a bunch of inputs from a single provider start to come in all close together. Then you could use those spikes, temporal spikes, to say, maybe this is a little anomalous. Another one is if it's an online learner that's constantly retraining, slow that down to maybe slow down the decision boundary shifting one direction or the other. And then finally, one that is super effective and one that we use all the time are gold standard queries. These are samples that you crafted yourself that each time the model retrains, they have to get these right. And that's kind of your keeping everything in check. If for some reason you don't get these right, something has gone terribly wrong. And honestly, that one, it's the most simplistic, but also the most effective way to do like a sanity check before rolling something out. I have a colleague, Hiram Anderson, who used the bottom tagline, and that's true. Like, labeling is super important. You have to have almost absolute faith in the labels that you get from your data provider, which can be incredibly difficult for things like malware or people's interpretation of malware. Any sort of crowdsourced data too is super messy and requires a lot of human attention. So things like active learning or active labeling become paramount to your success kind of in that area. So at the end of the day, you kind of have two approaches for these scenarios that I laid out. You have the left side of the screen, which is the more traditional red versus blue, where your data scientists are kind of kept in a vacuum, these classifier designers, and they're waiting for attacks to come in, and it's very reactive. We haven't started doing this at Endgame. We're actually going to try this in December, where we have a legit red team attacking our models while we try to understand what's going on in real time and devise countermeasures. I think that's going to go really poorly for my team, would be my guess. The other option, and one that we do employ on a semi-regular basis, is just like a purple team. Like Army of one, I create a model, I'm going to attack it, and then see how it goes, and then make modifications or develop countermeasures. So for red strategies, and I'll lay out blue shortly after this, you have a couple of different options. Are there red teamers in here by any chance? No? One? Yeah? All right. Thank you for raising your hand. Otherwise, it's going to be super awkward. You have a couple different options. Most of them are OSINT related. The easiest way is to see if it's publicly available, which is super nice. Things like VirusTotal, maybe vendor websites that they've set up just to let you test it out for Black Hat or RSA. Most of the time, vendors are relatively mum on their marketing materials about how their stuff works. But every once in a while, they'll let loose a nugget, like a blog post will squeak through that'll provide more detail. I recommend kind of reading those, learning terminology, and then using something like archive.org, which is a collection of all academic papers, and then you can start to look those terms up, get research, and a lot of times those will be paired up with really cool things like open source platforms and frameworks, and that's really nice. The other thing is, if you're interested in doing something like this, particularly to perturb malware or maybe create like exploit examples or something, it's really important to understand like how to perturb that malware. We use Leaf, which is a pretty nice way to edit a binary without breaking it. Backdoor Factory, which I think is defunct, kind of makes it easy, like Python easy, to identify code caves, which you can inject various bits of code in there to fool or stun a classifier. And then one that is actually super good, I guess, in the grand scheme of things. It's just appending a bunch of zeros at the end of a file, and sometimes that'll work. There was a paper that came out, I think, 2 months ago where they did that, and it worked like 40% of the time, which is not at all alarming, and just something that we as data scientists need to consider. Toolkits. So these are the things that make it super easy to do these red versus blue scenarios in a closed environment. Like I said, the malware ENV for Endgame, that was the kind of Atari-based simulator that we built. I recommend checking that out. Clever Hans, Fullbox, some of these others are done by absolutely brilliant kind of academics and researchers at Google Brain. Like I said, all these are available open source. They're all Python. They incorporate red and blue strategies. And I think you're going to see more and more kind of growing out of this, specifically for the InfoSec domain. Blue strategies. Like I said, this is seldom a feel-good story for blue teamers, but no silver bullets, really. Otherwise, this talk would have been significantly shorter. Hardening models at the end of the day comes at a cost of classification performance, and it's a cost that most vendors aren't willing to incur. So that's something that you need to consider on both sides of the house. It's just, you need to be right more often than you need to be secure, which is a bit of a bummer, but that's just the reality of the situation. Some things that you could do, though, is seek out like third-party testing and validation, so you can start to understand how your models hold up to scrutiny. As I said, labeling becomes super important, so you could do things like look at samples that sit right on those decision boundaries that may be a little difficult for your models to classify, and then have human experts review them and provide more steadfast, confident labels. And then at the end of the day, I would recommend just doing kind of this purple team approach where you build a model and then you attack it on your own. At a minimum, you'll start to understand some nuances and some unpredicted or unknown behavior of your model, which is always good to understand. If you're going to push it out to something like VirusTotal, we at Endgame do that too. I just recommend like maybe don't provide a score. Don't incentivize attackers with any more information than they need. Just doing like a traditional good bad will get the job done. And then finally, I guess just 2 questions that if we have time at the end, I'd be interested in hearing from the audience your thoughts. But like, do red team and blue teams kind of need a machine learning expert or a data scientist on hand as attacking these technologies becomes a little bit more in vogue? And then finally, is there really a difference between developing a adversarial example and just finding a false positive in the eyes of a machine learning classifier? What does that responsible disclosure process look like? This is a little bit different than the traditional vulnerability community, and it's something that I don't think anybody's really thought about because this is such a nascent field. And then finally, if the bulk of you here are just consumers of this technology, I definitely recommend the next time somebody comes knocking at your office door saying, ML will save you from everything, think about these questions. Like, don't be afraid to ask, where did they get their data? How do they label it? When they throw up things like 99.9% effective, what do they actually mean by that? Like, is it an accuracy thing, or is it actual classification performance? How often do they false positive on something? Does it generalize well to concept drift? So over time, do they run into any problems? Do they have to retrain more often because malware can change depending on the flavor of the week? These things, I think, and there was a great conversation a few months ago with swift on security, where he was being, I think, approached repeatedly by ML-backed vendors, and he just threw it out there. He's just like, what do? I have no idea what to ask, but I want to ask something. And a lot of these questions kind of came out of there, a couple blog posts we've done at Endgame, and they seem to resonate well. And at a minimum, you'll make an SE or salesperson sweat a little bit, which it's not the worst thing. But yeah, these are great questions. People should have the answers to these. They're not overly difficult, but it will provide you a little bit of information before you plop down some money. That's it. Any questions? Yes?
Yeah. Do you see machine learning as effective defense against like phishing attacks? It's such a human-based attack, and at least for the more sophisticated campaigns, they're so close to accepted and expected behavior. It seems like a tough model to train.
Yeah, so, man, it's almost like you work at Endgame. No. So we actually just rolled out something that was ML-backed for phishing. Part of it was just like looking at static features of like a Office document. And that's pretty effective in the grand scheme of things. The other thing that we're doing is applying deep learning and computer vision. So we're taking a screenshot of the image and then using something called YOLO, which is a very funny way of saying like you only look once. And it provides object bounding boxes of things like enable macro buttons or click here for finance reports, and we try to identify those. So when we present them to a SOC analyst, we say, hey, we know it's bad because of static features, but if you don't believe us, here's a screenshot with like circling it in marker, like here's exactly why it's bad. So it definitely can be done. I think other vendors are also doing some really cool stuff with that too, just in different ways. So yeah.
The adversarial examples that you generate yourself, have you looked to see what that does with other machine learning-based AV vendors and also with traditional signature and heuristics AV vendors?
Yeah, so we have. So the example, let me see if I can pull it up quick. So here, this was actually against real vendors. We took the samples that bypassed our little substitute model, I guess, and then threw them against VirusTotal just to look at kind of a before and after. So before we made the changes and then after. So we were able to actually evade a decent mix of both. AV vendors are starting to do a really good job with like heuristics. So they're just looking for maybe one thing, and if you don't change that one thing, then it doesn't really change anything at all, right? So I would say for the most part, they're relatively good at being resistant to that sort of problem, unless you make fundamental changes, like packing it. But if you just add an import here and change the section name there, I doubt that there's like a massive difference.
Has Endgame seen any intelligence or any information that actual APT campaigns or malware authors are trying to do this?
No. So I think that at Black Hat this year, and if anybody here attended that, I feel like IBM tried to create like a simulation of how like a large-scale actor would do this. I personally haven't witnessed this. I think what you'll see with like the rise of deep learning platforms and things like that everything's more accessible and it becomes easier to build these things. So it wouldn't surprise me at all if that becomes something that happens in the next maybe 18 months to 2 years. And I think that's it. We're out of time. I'll pop over here or go outside if people have anything else. But if not, that's it. Thanks.